Welcome to Strength of Materials N5. Today's presentation is on stress, strain, and tensile testing of materials. If you are new here, I will ask you to subscribe to this channel. Also, leave a like and a comment, as all of that helps promote our community, and it also encourages me to continue to produce content of this nature. Having said that, let's begin. First, I want to speak about forces and stresses. And the first type of forces I want to talk about is tensile forces. Tensile forces are forces that have a tendency to stretch the object on which they act. So let's say, for instance, you have an object that looks like this. If you apply forces like that, you can see that these forces will have a tendency to stretch this object. And so these forces will therefore be tensile forces. And the stress that arises from tensile forces is what we refer to as tensile stress. And the equation for stress, you are already familiar with it. Stress is equal to the force divided by the area. And the area that you have in that equation is actually the cross-section area. That is the area that you have in the equation for stress, okay? It's the cross-section area. And what is the cross-section area? The cross-section area is the area that you see when you cut through the object. Let's say you cut through the object through that line, okay? You can see the line that I have here. Let's say you cut through this object where that line is. And so if you do that, the cross-section area that you will see is a rectangle, okay? I hope you can see that. If we cut through this object where the line is, okay, if we cut through and we get rid of the top part and we look at the area that is revealed, you will see that the area is actually a rectangle. Okay, so the area of this rectangle is the cross-section area of this object where that line is. Okay, so in this equation of stress, which is equal to the force divided by the area here is the cross-section area. So if you were to calculate the stresses where this line is, the value of this area will be the area of this rectangle because that's the cross-section where the line is. But you may have to find the stresses at another location, for instance, where this other line is. Okay, so if you have to calculate the stresses where this line is, you can again imagine cutting through the object where the line is. And if we do that, what will be left of the object is something like that. And so the area that is revealed, or the area in contact with the cut from the object, will be that. Okay, you can see you will have this area here, which will be here because we cut through, and in the middle here it's empty, so there is nothing. And then you will have this area somewhere here because we cut through where the line is. And so this area plus that area, that is what will make your cross-section area. Okay, I hope that is clear. And so you really need to be careful and clever enough to be able to visualize in your mind what the cross-section area will look like at various locations whenever you need to calculate the stresses. The next type of forces that we have is what we refer to as compressive forces. And these are forces that have a tendency to compress the object on which they act. And so let's say you have this tube, okay, this cylindrical tube. And so if we apply compressive forces on it, it will look like that. And as you can see, these forces have a tendency to compress this cylindrical tube, okay? And so the stresses that arise from compressive forces are what we refer to as compressive stresses. So the equation for the compressive stress is the same as the equation for the tensile stress. It's equal to the force divided by the area. And again, the area here is the cross-section area. And so in the case of this cylindrical tube, you can see that the cross-section area is uniform throughout. Okay, it's the same throughout. It doesn't matter where we cut it, we will have the same cross-section. And so the cross-section area will look something like that. As you can see, it is a circle with a hole in the middle. Okay, and so this is what the cross-section area of this tube looks like. Finally, the type of forces that you need to know, at least for this module, is what we refer to as shear forces. So now, what are shear forces? Let's say you have two wooden planks that have been glued together. Okay, so you can see you have the top plank here and you have the bottom plank here. Okay, the bottom plank is here, the top plank is there, and these two planks are glued together. Okay, so I'm gonna draw a line there to show you where the glue is. And so this is the glue that joins these two planks. Okay, now if we apply forces in that direction, as you can see, one to the left and the other to the right, then you will see that the glue here will be in shear, okay? Because it will have a tendency to like spread because of the direction of the forces that are acting on these two wooden planks, okay? So the glue here will be in shear. And so this is what we refer to therefore as shear forces, forces that have a tendency to shear a certain contact surface. Okay, so that is what we refer to as shear forces. And the stress that arises from shear forces is what we refer to as shear stress. And shear stress is also equal to force over area. But in this case, the area is not the cross-section area. The area in question here is what we refer to as the shear area. And in this case, since we're dealing with two wooden planks, this shear area will be the area at the contact surface, okay, where the glue is. And if you can picture it in your mind, you will see that that area is rectangular, okay, because you're dealing with two wooden planks that have been glued together. If you look at the area of the contact surface, it is a rectangle, okay. So that is the area that you will use in your calculations for stress, okay? When you do stress is equal to force over area, the area in question when you're dealing with shear stress is the shear area, okay? I hope that is clear. And so, the tensile stress and the compressive stress are often referred to as direct stresses, okay? So if you come across the expression direct stress, it is referring either to the tensile stress or the compressive stress, okay? So if in a question they ask you to calculate the direct stress, just know that you have to calculate either the tensile stress or the compressive stress, okay, depending on whether you have tensile forces or compressive forces acting on that particular object in the question, okay? So do not be surprised if you hear the expression direct stress. This is just referring to either tensile or compressive stress, okay? Very, very important. And before I move on, I also need to remind you of something because you know that stress is equal to force over area, okay? Direct stress is equal to force over area, and this area is the cross-section area. So that means that if this area is small, the stresses are going to be big because you're dividing by a small number. Okay, so the stresses are going to be big. Therefore, we can conclude that direct stresses are maximum where the cross-section area is the smallest. Okay, very important. You get maximum direct stress where the cross-section area is the smallest. It's very important to remember that, because sometimes you get a question where they ask you to find the maximum stress in the object, and so you need to look for the place where the cross-section area is the smallest, and that is where you will have your maximum stress. Now, let us speak about direct strain and shear strain. First, we will speak about the direct strain and its connection to the Young's modulus. Let's say you have these two bars. You can see the bar on top and the bar at the bottom, and these bars have been planted inside of a wall. And the length of the bars is M. And now, let's say you apply a tensile force to the top bar, like that. Because of this tensile force, you can expect the bar to stretch, okay? As you can see, the force is acting from left to right. So, of course, since this bar is planted inside of the wall here, this force, therefore, will have a tendency to stretch this bar, okay? And even if you cannot see the stretching with the physical eye because it's so small, but there is a stretching that takes place when you apply a tensile force to a metallic bar, okay? And so in this case, let's say it stretches like that, so that the discontinued lines here are showing you the final position of the bar, okay? So it's stretched like that, okay? You can see the discontinued lines that are showing you the final position of the bar. And so this distance there, that is the distance the bar stretched by, okay? And so the strain, the direct strain, is therefore equal to X divided by L, okay? We use this Greek letter, it's epsilon, for strain, direct strain, and it is equal to X. X here is the stretching of the bar, the length by which it's stretched, divided by the original length of the bar, okay? And X in that case is referred to as the elongation of the bar. So I hope you can clearly see what is going on here. We have a bar and then we apply a tensile force to the bar. Because of this force, the bar stretches by a length X. And so if we want to calculate the direct strain due to that force, that strain will be equal to this stretching, which we refer to as elongation, divided by the original length of the bar. Okay, now for the bottom bar, let's apply a compressive force, okay, like that. And of course, because of the compressive force, this bar here is going to become shorter. And let's say that the far right end of the bar will move to the left until it reaches the place where you see these discontinued lines, okay? So it has moved like that, okay, because of this force that has compressed the bar. And so, as you can see, the original length of the bar is L, and so now it has been compressed by a length X again. And so if we have to calculate the strain, once again, the direct strain is equal to X divided by L. But in this case, X is not an elongation, it is actually a shortening of the bar, because under compressive forces, the bar becomes shorter. Okay, so X is the shortening. However, the direct strains equation still remains the same. Okay, it's equal to X over L. And so, what is the connection between strain and Young's modulus? Okay, this is the connection that exists between strain and Young's modulus. Basically, direct stress is equal to Young's modulus multiplied by strain. And I need to point out here that strain is dimensionless because you are dividing a length by another length. So strain does not have a unit, okay? It is dimensionless. Very important to remember that. It's very simple to see because when you divide the length by another length, of course, the units will cancel. And so in this case, I was speaking about the connection between between strain and Young's modulus, and that is through this equation, okay? Direct stress is equal to Young's modulus multiplied by strain, okay? That is what it is. We use the letter E to refer to the Young's modulus. It is also referred to as the modulus of elasticity, okay? And so it's very important for you to remember that. This Young's modulus just gives you an idea of the resistance of the material to stretching or to compression, okay? The larger the Young's modulus, the more difficult it is to stretch the material or to compress it, okay? So that is what the Young's modulus is. So remember this equation, it's a very important equation. Stress is equal to Young's modulus multiplied by strain. And from this, we can derive another equation that is very important. You will remember that stress here is equal to force divided by cross-section area, okay? And you will remember also that strain is equal to X divided by L, okay? So if we replace the direct stress and the strain by what they are equal to, what you get is something like this, okay? And from this, then you can get an equation for X, okay, which is really going to be useful in this module, okay? So if you rearrange this equation, you can then write that X is equal to FL divided by EA. Okay, so this is an equation that is very, very important because it allows you to calculate the elongation or the shortening, depending on the question, based on the force and the original length of the object, the Young's modulus, and the cross-section area of the object. Okay, so this here is a very important equation to remember. X is equal to FL over EA. Very, very important. Now, let us speak about the shear strain and the modulus of rigidity. And so, the shear strain, for you to understand how we get it, you need to look at this object here. You can see we have an object there, and the vertical side of the object is L, okay? So that's the measurement for the vertical side of the object. Okay, the horizontal side is not of importance in finding the shear strain, but it's the measurement of the vertical side of the object that is important. So let's say in this case, the vertical side of the object here has a length of L, okay? That is the measurement of it. And so if we apply a shear force like that on the object, of course, you can imagine what will happen to the object. If the bottom part is held fixed, okay, then the top part will move to the right like that, okay, because of this shear force F that is applied on the object. And so now, this distance here, we will refer to that as delta X. That is the distance by which the object moved to the right. We will call it delta X. And so the angle that you have here, let us refer to that as theta. And as you can see, if you look here, we have a right angle triangle, okay? So now, the shear strain is actually tan of theta, okay? So therefore, shear strain is going to be equal to delta X divided by L, and that is equal to tan of theta. If you understand properties of a right angle triangle, you will see that this is theta. This side here is L because, as I said earlier, this vertical side has a length of L. So this is L, and this is delta X, and this is theta. Tan theta is delta X divided by L. Opposite side divided by adjacent side, okay? And so if you do that, that is tan theta, and this tan theta is actually the shear strain. So what is important for you to remember is that shear strain is equal to delta X divided by L. And you saw from this picture how you measure delta X and how you measure L, okay? Very, very important. And the relationship between the shear strain and the modulus of rigidity is given by this equation. Okay, so shear stress is equal to modulus of rigidity. It is also called the shear modulus. Okay, and that multiplied by the shear strain. Okay, so shear stress is equal to shear modulus multiplied by shear strain. Okay, and this shear modulus is also referred to as the modulus of rigidity. Okay, very, very important. And so, having done that, let us move on to the first example. So this is what we have here. The question says the clamped object below is made of two parts that have square cross sections. Okay, so this part of the object has a square cross section, and this part of the object also has a square cross section. And this object is clamped. It means it is held by a clamp. Okay, this is the clamp that you see here in black on the far left. Now, question 1, you need to find the maximum stress in the object when the force F is 15 kilonewtons. Question number 2, you need to find the value of F when the minimum stress recorded is 10 megapascals. So let us go ahead and solve this question. So for question number 1, what we need to do is to find the stress in the object, where the maximum stress in the object when the force is 15 kilonewtons. Now, for you to find the maximum stress, as I said earlier, the maximum stress occurs where you have the smallest cross section. And as you can see, this object is made of two parts. And the place where you will have the smallest cross section is here, because here the cross section area is smaller than the cross section area that you have here. And remember, you are told in the question that the cross sections are square. Okay, so since here we have the smallest cross section, that means that this is where we will have the maximum stress. Now, for question number 1, the value of the force is given as 15 kilonewtons. So therefore, we will use that to get the stress. But first, let us find the smallest cross-section area. And it's going to be equal to this. As you can see, I have changed my dimensions to meters, because you know in engineering dimensions are given in millimeters. Okay, and so you need to change that to meters. 50 millimeters is 0.05 meters. And since the cross section is square, to get the area, you just need to multiply the side by itself, or to square the side. Okay, the area of a square is equal to one of the sides squared. Okay, and so in this case, it's 0.05 squared. And when you do that, you get the cross-section area as 0.0025 square meters. Okay, and that is the smallest cross-section area. Why do we need the smallest cross-section area? Because that is where you will have the maximum stress. Now, having this area, we can then use the stress equation, and we will plug in the numbers. So the force is 15 kilonewtons, and the area we just calculated is this one. Okay, that's the area in question. That is the smallest cross-section area. And once we do the calculations like that, we end up finding that our maximum stress that we can have is 6 megapascals, okay, when the force is 15 kilonewtons, okay. So if you apply a force of 15 kilonewtons, the maximum force that you will have in the object is actually 6 megapascals. I hope that is clear. And so for question number 2, now they tell you find the value of F when the minimum stress recorded is 10 megapascals. Okay, so you can say F is 15. F was equal to 15 for the first part of the question. For the second part of the question, it's a completely different problem. We do not know what F is, but we do know that the minimum stress that we have is 10 megapascals. Now, for this object, where is the minimum stress gonna occur? The minimum stress is going to occur where you have the largest cross section, okay? The maximum stress occurs where you have the smallest cross section, but the minimum stress occurs where you have the largest cross section, which is here, okay? So we need to find the biggest cross section area, and it's equal to this. Again, the dimensions are in millimeters. I changed that to meters, and because it's a square cross section, I had to square it to find the cross section area. So the biggest cross section area is this 0.01 square meters. And I can find, therefore, the force from the stress equation. You will remember stress is equal to force over area. And so from this, we can then write that the force is equal to the stress multiplied by the cross-section area. In this case, the cross-section area of interest is the biggest cross-section area which we calculated earlier. Okay? And so we know that the stress is 10 megapascals, so we will multiply 10 by this cross-section area to find the force that we are looking for. And so if we do that, this is what we get. And as you can see here, the stress is 10 megapascals. So when I'm plugging in the numbers, I need to do 10 times 10 to the 6 because that is what mega is, okay? Don't forget to do that. I've seen students just plugging in 10 and they forget that it's written 10 megapascals, okay? Because it's 10 megapascals, you need to write 10 multiplied by 10 to the 6. It's not just 10 because the SI unit for pressure and stress is pascals, okay? Very, very important. And so here you need to do 10 times 10 to the 6 and you multiply that by the area and that gives you the force like that in newtons, and then you can write it in kilonewtons as 100 kilonewtons. And so that's all that you needed to do for this question. Let us look at another example. Now, a cable shackle, as shown below, uses a bolt with a diameter of 10 millimeters to connect the hook to the load. If the load to be lifted has a mass of 300 kilograms, calculate the shear stress experienced by the bolt. Okay, so now we have a situation like that. They even gave you a beautiful illustration with a picture here. And you have this mass of 300 kilograms that is hanging, connected to this ring, and the ring is connected to this bolt, and all of that is placed on a hook. And now they ask you to calculate the shear stress in the bolt. So how are you going to do that? And so the way you're going to do that is to first of all remember the shear stress equation. The shear stress equation is force divided by shear area. Okay, the area here is the shear area. Now you need to look at the picture carefully for you to understand what will the shear area be. Okay, the first thing that we know is that on the ring here, okay, on the ring here, you have the weight due to this mass that is acting on the ring. So we can draw it like that. Okay, this is the weight that is due to this mass of 300 kilograms. It's acting on the ring at this point. Okay, you can just simplify the drawing, remove all of this, and put an arrow for the weight there. Okay, and now once you have that, now the big question is, what is the shear area? And as you can see, the shear area is here, okay, on the bolt, okay. It's not on this ring that you have the shear area. The shear area is on the bolt, okay, but it is here where the ring is connecting with the bolt, and also there, okay. That is where you have your other shear area. Okay, so you have one shear area here and you have another shear area there. That is why a question like that is sometimes referred to as a question of double shear, because you have an object that is in shear at two different locations, okay? So here, this shear area on the bolt is, you have this shear area on the bolt, and you also have that shear area on the bolt, okay? And the load that is acting on the bolt is this weight due to that mass of 300 kilograms. So let us go ahead and find the value of this load, okay? So F, which is equal to the weight, okay, will be equal to 300 multiplied by 9.81. So what you get is 2,943 newtons, okay? So that is W, and that is also the value of F that you will use in your shear stress equation. Now we need to find the shear area. And if you look at this bolt here, you know that a bolt has a circular cross section. Okay, so if you look at this bolt, the cross section, of course, is a circle, as you can see here. Okay, the cross section of this bolt is a circle. And in this case, we have shear at two places. We have shear here. Okay, so you will have that cross section there, which is a circle, and then you have shear again here. So you will have again the cross section of the bolt there. Okay, so therefore it's twice the area of the circle that is the area that is in shear, because you have the area here and you have the area there. Okay, so now the shear area therefore will be equal to twice the cross section of the bolt. Okay, so in this case it's twice pi by 4 multiplied by the diameter of this bolt squared. Okay, as you see on the screen. And we know that the diameter is 10 millimeters. You convert that to meters, that is 0.01, okay? And so you square that because that's how you get the area, and you multiply it by pi by 4, and then you need to multiply all of that by 2 because we have double shear, okay? We have shear here and we have shear there. The area here is in shear, the area there is in shear. And so once you do that, the value of the area that you get is 157.08 multiplied by 10 to the minus 6 square meters. And so that's the shear area, okay? You have two shear areas, so you need to sum them together, okay? That is why we took one shear area and multiplied by 2, because these shear areas are identical, okay? This shear area and that one are identical. So summing them is like multiplying 1 by 2, okay? Very important. So once we have the total shear area, okay, we can then find the shear stress by dividing the force by that shear area. And what you get for the shear stress is going to be a very long number, okay? But if you convert it to megapascals, then you will get 18.736 megapascals. Okay, of course, when you do these calculations here, you are in SI units. So it will give you a very long number in pascals, but then you can convert it immediately to megapascals. And what you will get is 18.736 megapascals. Now, let us look at an example that is more like what you get in your exam. Okay, so the first part of the question, define direct stress, that I will leave for you to do as a homework. I am going to focus on the second part of the question, okay? So the second part, 1.2, a steel rod shown in figure 1 below has a length of 61 centimeters and a diameter of 50.8 millimeters. A center hole with a diameter of 25.4 millimeters is drilled from one end to a depth of 10.16 centimeters, okay? A compressive force of 200 kilonewtons is applied to the rod. Take the Young's modulus equal to 200 gigapascals. Now, you have to calculate the stress in the hollow part. The hollow part is here. Okay, so basically you have this object, but on the one side there is a hole that has been drilled in the object, and this is the hole that has been drilled in the object. For those of you who have done engineering drawing, you can understand a drawing like this, okay? You can see that these discontinued lines here are to show that there is a hole that has been drilled inside of the object. But you can see that the hollow part does not go throughout the object, okay? It stops here, okay? So the object is only hollow for a length of 10.16 centimeters, okay? Because from here to here, the object is full, okay? It's not hollow on this side. It's only hollow here. Okay, so now they want you to find the stress in the hollow part, and then they want you to find the stress in the solid part, and then they want you to find the total change in length. You can see that you have a 200 kilonewton force that is pressing on the object. Okay, so the object is going to be compressed. So they want you to find the total change in length. In other words, the total shortening of the object, okay? And then finally, the final length of the rod, okay? And so let us go and do this question. So for question 1.2.1, we need to find the stress in the hollow part. Now the hollow part is here, as you can see. And so for us to be able to find the stress in the hollow part, we need to find the cross-section area of the hollow part, okay? And to find the cross-section area of a hollow cylinder, it's simply pi by 4 multiplied by the outer diameter squared minus the inner diameter squared, okay? You know this equation. And so this is how we will find the cross-section area of this hollow part. Okay, the outer diameter is given to us as 50.8 millimeters. You change that to meters, that will give you this. The inner diameter of the hollow part is given here as 25.4 millimeter. You change that to meters, then you have that here, and you need to square it because that is what the equation requires. And so once you do that, then you find that the cross-section area of the hollow part will be equal to 0.00152 square meters. Okay, we always work in SI units. Do not forget. So you need to change the dimensions to meters. Okay, from millimeters to meters. And so in this case, you get the area as 0.00152 square meters. Okay, that is the cross-section area of the hollow part. Okay, the reason we used this equation is because you have a hollow cylinder here. So the cross-section of a hollow cylinder is given by that equation. Pi by 4 multiplied by the outer diameter minus the inner diameter. Okay, of course, you square the diameters. And that is what gives you the area, okay? And so, once we have the cross-section area of the hollow part here, then we can find the stress in the hollow part. The equation for the stress is force over cross-section area. And the force that we have here is 200 kilonewtons. Again, you need to change that to SI units. So you need to work with newtons. So it's going to be 200 times 10 to the 3 divided by the cross-section area of the hollow part, which you plug in here. And this again will give you a very long number in pascals. But if you convert it to megapascals, that number will then be 131.579 megapascals, okay? I did not want to write the long number that are found in pascals and then write the conversion, okay? You can do that yourself, okay, while you're checking my answers. But I just went straight ahead and converted the answer that I got to megapascals immediately. Okay, but the answer that this will give you will be an answer in pascals because we are in SI units. And as I said, I repeat, it's going to be a very long number. But if you convert that number to megapascals, then you will get this here. So I jumped a step here. I just got my answer in megapascals. Okay, so this is the stress that you have in the hollow part. The stress that you will have in the solid part, the full part, the solid part is here. There are no holes. Okay, and so you know what is the diameter of the full part, so you can get the cross section of the full part. And if you do that, then you can plug it into the stress equation to find the stress of the solid part. And so the force again is 200 times 10 to the 3 because it's 200 kilonewtons. The area of the solid part is pi by 4 multiplied by the diameter of the solid part squared. The diameter of the solid part is all of this, okay? And it's shown here as 50.8 millimeters. You change that to meters, that is 0,0508 meters. That is the diameter of the solid part, all of this. And so if you square that and multiply that by pi by 4, that gives you the cross-section area of the hollow part. Sorry, of the solid part, the cross-section of the solid part. And so the stress, therefore, is equal to the force divided by the cross-section of the solid part, okay? That gives you the stress in the solid part. And so if you do that, what you get, again, this will give you a very large number, but you change that to megapascals and you will get 98.676 megapascals. That is the stress in the solid part. For question 1.2.3, they want you to find the total change in length. Now, what you need to understand here is that when you begin to apply this 200 kilonewton force on the object, it will cause the object to compress because this is a compressive force. So this object is going to become short, okay, by a certain amount. In this case, as you can see, the object that we have here is not uniform throughout. Okay, this object is not uniform throughout. So for us to be able to study the change in length of the object, we need to look at this object in two different portions. Okay, so the first portion of the object will be this, or we may call it the first part of the object will be the solid part. And the second part of the object will be the hollow part, okay? Because this object is not uniform throughout, okay? The object is not solid through, or it is not hollow through, okay? Part of it is solid and part of it is hollow, okay? So this object is not uniform in its composition. Therefore, we need to look at it in parts. We need to look at it in segments. Okay, if we want to find the total change in length. So the first segment will be the segment where the object is solid. So let us call this segment 1, okay? The first part of the object where it is solid, let us call this part 1, okay? And it goes from here to here. Okay, that is the first part of the object. And the second part of the object is where the object is hollow. And it goes from here to here, okay? And we will call that part 2, okay? So now, the total change in length of the object will be equal to the change in length of 1 plus the change in length of 2. And in this case, these are shortenings because this force is a compressive force. So this segment 1 here will compress by a certain amount, and segment 2 will also compress by a certain amount. Now, the total change in length of the object will be the sum of the compressing of 1 and of 2, or if you want, the sum of the shortening of 1 and of 2, okay? Because they are not going to shorten in the same way or at the same rate because these two parts of the object do not have the same composition. One is hollow and the other is solid. Okay, so but to get the total shortening, you need to add the shortening of 1 to the shortening of 2. Okay, I hope it is making sense. So the total shortening xt is going to be equal to x1. x1 is the shortening of 1 plus x2, which is the shortening of 2. Okay, because as this force is applied, this first part is going to become short by a certain amount, and the second part of the object is also going to become short by a certain amount, but it's not going to be the same amount. However, the total shortening of the object is the sum of the two shortenings. I hope that is clear. And so we need to find the total change in length. In this case, it's a shortening, the total shortening. And that is going to be equal to the shortening of 1 plus the shortening of 2. Now, you will remember the equation for shortening that I gave you earlier of x is equal to FL over EA. And so, in this case, for x1, we will use the subscript 1, and for x2, we will use the subscript 2. So therefore, we can say that xt is equal to F1 L1 over E1 A1. And that is for x1, okay? We're just using this equation, but we are adapting it to x1 plus x2, and we will use this equation. So x2 will be equal to F2 L2 divided by E2 A2. So we can say xt is equal to that. But there are a few things that you can observe here. The force that is acting on 1 and on 2 is 200 kilonewtons. Okay, so the F1 is equal to F2. Okay, we can see that. It's not a different force that is acting on 1 and another force acting on 2. Okay, it's the same force. So F1 is equal to F2. And also, 1 and 2 are made of the same material, therefore they have the same Young's modulus. Okay, it's not two different materials. These two parts of the object are made of the same material. The only difference is that the second part of the object is hollow, but it is made of the same material. Therefore, E1 and E2 is the same. Okay, so E1 is equal to E2. And so once you understand that, then you can go ahead now and plug in the numbers to solve for xt. Okay, so if you do that, this is what you're going to get. Okay, so xt is equal to F1. F1 is equal to F2 is 200 kilonewtons. So we have 200 times 10 to the 3 because we work in SI units, multiplied by L1. L1 here is the length of the first part of the object. If you look at the length of the first part of the object is 50.84 centimeters. You change that to meters, this is what you get. Divided by E1. E1 is 200 gigapascals. It's the same as E2 because they are made of the same material. So 200 giga. Giga is times 10 to the 9. So you multiply like that. This is what you get. 200 times 10 to the 9 multiplied by the cross-section area of segment 1. The cross-section area of 1 here is this area there, pi by 4 multiplied by that diameter. Okay, that is the area of segment 1, the cross-section. And if you do this multiplication, the number that you will get in square meters is this. Okay, so that is the area of 1. Plus F2 is equal to F1, 200 times 10 to the 3. L2, the length of the second segment, is what you see here. That is the length of the second segment. Okay, and you change that to meters, that gives you this, divided by E2. E2 is equal to E1 because they are made of the same material. So it's 200 times 10 to the 9, multiplied by A2. A2 is the cross-section area of the hollow part, okay, the second segment of the object. And the cross-section area of that we calculated earlier, this is it here. And so that is what you have here, okay? And so when you sum this, what you end up getting for the total change in length is 317.677 times 10 to the minus 6 meters. And if you change that to millimeters, is 0.3177 millimeters. Okay. And now for question 1.2.4, you need to find the final length of the object. And as you can see here, it is a shortening. So finding the final length, therefore, will be taking the initial length of the object and subtracting from that the shortening. We just calculated the total shortening of the object. And so for us to get the final length, we will take the initial length of the object and deduct from that the shortening, because this is a compressive force. So the object, the final length of the object will be smaller than the initial length. And so if you do that, then you will see that the final length of the object, which are called LF, will be equal to this plus that. This plus that is this here plus that. Okay, that is what gives you the original length of the object. And I am doing my calculations in millimeters. As you can see, 50.84 centimeters is 508.4 millimeters. Okay, so I took that plus this, and then to that I subtracted the shortening, okay, because this is the total change in length. It is a shortening, and so we need to subtract it from the original length of the object for us to get the final length of the object. And if you do that, what you get is 609.6823 millimeters. This is what the final length of the object is going to be. Let us look at this example now. Refer to figure 1 below and calculate the following. As you can see in this figure, the force that is acting on the object is a tensile force. Okay, so if there is a change in length here, it's going to be an elongation. Okay, it's going to be an elongation. Okay, the object will increase in length. We just looked at an example where the object became shorter because of compression, but in this case it is a tensile force that is acting, so the object is going to increase in length. Okay, and as you can see, this object is also made of two segments that do not have the same cross-section area. Okay, so if we have to study the change in length here, we will need to also look at this object in two parts. Okay, it's very important to notice that already when you are looking at the question. Now for question 1.1, they want you to find the diameter D if the stress is not to exceed 160 megapascals. Okay, if the stress is not to exceed 160 megapascals, it means that the maximum stress that this object can reach is 160 megapascals, and they want you to find the diameter D. Okay, now for question 1.2, they want you to find the length L if the total elongation of the rod is 0,165 millimeters. The length L is the length of this segment here. You can see it's written L millimeters. The length of this segment, that is what they call L. But they gave you the total elongation due to these forces. Okay, the total elongation is 0,165 millimeters. They gave you the Young's modulus of the material as 200 gigapascals. So let us go ahead and try to do this question. And so for question 1.1, you need to find the diameter D if the stress is not to exceed 160 megapascals. The fact that they told you the stress is not to exceed 160 megapascals, it means that the maximum stress that the object can carry is 160 megapascals. Now, we know that stress is maximum where the diameter is the smallest, or where the cross-section area is the smallest. In this case, the stress will be maximum here because that is where you have the smallest cross-section. You can look at the way the drawing is looking. You can see that where the diameter is D, that's where you have the smallest cross-section. So you need to find that value for D. But we know the equation for stress. Stress is equal to force over cross-section area. In this case, the cross-section area where the cross-section is the smallest is here. So it's going to be given by pi by 4 multiplied by the diameter here. We don't know what it is. It's D, so we just write D squared. And so force divided by this cross-section area will give us the maximum stress, okay, which is already given as 160 megapascals. Okay, so we go ahead and we plug in the numbers because we have this maximum stress, we have that force, we know it, 80 kilonewtons. So the only thing we do not have is the diameter, and so if we plug in the numbers, this is what we get. And as you can see, the only thing that you do not have here is the diameter. And so you can easily get the diameter and you will find it to be equal to 0,025 meters, which is equal to 25 millimeters. Okay, so that is the diameter of this segment. Now, for question 1.2, we need to find the length L. Okay, the length L is the length of this segment here. Okay, that is L. We need to find that length if the total elongation of the rod is 0.165 millimeters. Okay, and they gave you the Young's modulus. Now, what you need to understand here is that, again, this object is made of two segments that are not uniform, okay, because they do not have the same diameter. So the way this segment is going to stretch because of the force is not the same way this segment is going to stretch, okay? But the total stretching of the object will be equal to the stretching of this segment plus the stretching of that segment, okay? And so let's call this segment 1, okay? And the other segment there, we will call it 2. And then we will say the total stretching of the object will be equal to the stretching of segment 1 plus the stretching of segment 2. And again, you will remember that elongation is equal to FL divided by EA. So we are going to adapt this to 1 and adapt this to 2 when we are plugging in the numbers. Okay, and so if you do that correctly, this is what you are going to get. Okay, we know that the total elongation is 0,165, so X total is 0,165, but because it's in millimeters and we're working with SI units, you need to change it to meters. That is why you see me, I multiplied it by 10 to the minus 3. And this will be equal to F1. F1 is equal to F2. It's the same force, okay? It's 80 kilonewtons. And so it's going to be equal to 80 multiplied by 10 to the 3 multiplied by the length of the first segment. The first segment is 120 millimeters. So to change that to meters, that gives you 0.12 divided by E. E is the same. E1 is equal to E2, so it's 200 gigapascals multiplied by the area, the cross-sectional area of 1, okay? And the cross-sectional area of 1, we know what is the diameter of 1, of segment 1. So to find the cross-section area, it's pi by 4 multiplied by the diameter squared. Again, I changed the diameter to SI units. It's in meters, okay? 0,04 meters squared, okay? That is what we have. And then you do that again for X2, okay? F2, L2 over E2, A2. So F2 is the same as F1, 80 kilonewtons. L2, what is L2? The segment 2 is here. L2 is the length of the segment 2. The length of the segment 2, it's called L. Okay, so that's why we have L here. Okay, divided by E2, which is equal to E1, 200 gigapascals, multiplied by the cross-section area of segment 2. The cross-section area of segment 2 is here. The diameter of segment 2, we found it, is 0.025 meters or 25 millimeters. So having that diameter, we can then calculate the cross-section area of segment 2 like that. And again, remember to use SI units. And as you can see in this equation here, the only thing that we do not have is L, that length L here, which is the length of segment 2. We do not have that, but that's what we have to find. So you can just solve for L. And if you do everything correctly, you will find L to be equal to 0,15561 meters. And you can just round it off to 156 millimeters. Now let us look at this example here. The compound bar shown in figure 2 is used in a machine frame and consists of a parallel steel bar and a copper bar. Now in this question, you have two bars that are not made of the same material. So when you have two bars that are not made of the same material, already you need to know that the Young's modulus is different. So E1 is not going to be equal to E2. Okay, very important to notice that already. Now, the compound bar undergoes a compressive load of 65 kilonewtons and is 127 millimeters long. The steel bar and copper bar are equal in length. Okay, so the length of the steel bar, this is the steel bar on the left and the copper bar is on the right. Okay, they both have the same length, 127 millimeters. And the load that is applied on them is 65 kilonewtons. Now you are told that the steel bar has a diameter of 15 millimeters and the Young's modulus of steel that you will use here is 215 gigapascals. The copper has a diameter of 20 millimeters and a Young's modulus of 145 gigapascal. Okay, so question 2.1.1, you need to find the stress that is developed in each material when they are loaded by this 65 kilonewton force. And then question 2.1.2, you need to find the final length of the compound bar. Okay, they meant the compound bar under the given conditions. Okay, very interesting question. Let us jump right into it. So now, for question 2.1.1, we need to find the stress that is developed in each material when loaded by 65 kilonewtons. Now, here I need to draw your attention to something. One thing that I've seen students do is that they will take this force of 65 kilonewtons because they know the equation for stress. Stress is equal to force over area. So they will take this 65 kilonewton force and they will divide it by the cross-section area of the steel. And when they do that, then they tell you that is the stress in the steel. And then they take again the 65 kilonewton force and they divide by the cross-section area of the copper. And then they say that is the stress in the copper. If you do that, that will be a mistake. In this case, the force that is in the steel is not the same force that is in the copper. Okay, you can imagine two people that are standing under a table and lifting a table. Okay, just picture that. Imagine two people under a table and those two people are lifting that table. Okay, if the table has a weight of maybe 100 newtons, let's say the weight of the table is 100 newtons and two people are lifting it and they're under that table and they're lifting that table, you cannot tell me that those people are both lifting each 100 newtons. Okay, that's not the case. Each of them is lifting a certain percentage of that load, but what they are lifting together is going to be 100 newtons. I hope I am making myself clear. Okay, so in this case, the steel bar will be carrying a portion of the load, not the whole 65 kilonewtons. No, it will carry a certain percentage of the 65 kilonewtons, and also the copper bar will carry the remaining percentage of the 65 kilonewtons. But together, they will carry the 65 kilonewtons. So the load that is carried by the steel bar plus the load that is carried by the copper bar, that is what will make 65 kilonewtons. It's like two people that are lifting a table, okay? They will not all lift exactly the same weight, but what they will lift when you put it together will be 65 kilonewtons, okay? It's the same scenario that you have here. Okay, so do not make the mistake of taking 65 kilonewtons and you divide it by the cross-section area of the steel to find the stress, and then you take again 65 kilonewtons, you divide it by the cross-section area of the copper to find the stress in the copper bar. Okay, if you do that, you will be making a mistake, because the steel is not carrying 65 kilonewtons. It's carrying a certain percentage of 65 kilonewtons. And the copper is carrying whatever remains. But together, when you sum what they carry together, that is when it is 65 kilonewtons. Think of it as two people that are lifting a table. okay? You cannot say that they are each lifting the total weight of the table, okay? They all are lifting a percentage of the weight of the table in such a way that when you sum what this one is taking and what that one is taking, then you get the total weight of the table. I hope it is making sense. Okay, having said that, now we will call the steel bar 1, okay, because we have two bars here, so we need to label them when we do our calculations. So the steel bar we will call 1, and the copper bar we're going to call it 2. And so one thing that we know is that the load that is carried by the steel bar, which is F1, plus the load carried by the copper bar, F2, will be equal to the total compressive load on the system, okay, which is 65 kilonewtons, or if you want, 65,000 newtons. Now, having said that, now you will remember that in this case, if you look at it carefully, you will see that these two bars are in parallel, okay? They're not in series, okay? The steel bar and the copper bar are in parallel. And because they are in parallel, when you compress them, they will shorten both by the same amount, okay? Because these are two bars in parallel, okay? They have the same initial length, and so when the load compresses them, they will both compress by the same amount, okay? So the shortening of the steel, which is X1, will be equal to the shortening of the copper, okay, the copper bar, which is X2. I hope you can see that here. You can see you have this bar and then you have that other bar there, okay? And these two bars are cylindrical and they have the same length. And so the load is applied on top of them both. So if it compresses both bars, it will compress them by the same amount. Okay, so the shortening of the steel bar is equal to the shortening of the copper bar. Okay, now what does that mean? You will remember the equation for shortening. And so if we adapt it to the steel and the copper, okay, so this is what we will have, okay? X1 will be F1L1 divided by E1A1. This must be equal to F2L2 divided by E2A2. Now, in this case, F1 is not equal to F2. I explained that earlier, okay? F1 is not equal to F2. But when you sum them together, then you get the total load that is compressing the system, okay? So in this case, F1 is not equal to F2. However, L1 is equal to L2, okay? L1 is equal to L2. The length of the steel bar is equal to the length of the copper bar. Now, E1 is not equal to E2 because you're dealing with two different materials. You have steel and then you have copper. They have different Young's moduli. Okay, so that's what you can see here. For steel, it's 215 gigapascals, and for copper, it's 145 gigapascals. Okay, and also because they have different diameters, their cross-section areas will not be equal. Okay, so now we will plug in the numbers. Okay, of course you can simplify it like this because of L1 is equal to L2, so you can just cross that out. It will simplify because these two are equal, so you can simplify it like that. And then now from there you can even find an expression for F1, okay, in terms of F2. And then from here now you can plug in the numbers because we're trying to find the stresses that are developed in each material, and for that you need to find the force that is acting on each material. So we need to find F1 and we need to find F2 because the equation for stress is force divided by cross-section area. So for you to be able to find the stress, you need to know what the force is. We already know what the cross-section areas of these two bars are, but we do not know what are the forces in the steel and in the copper. So we need to find that. And that is why you see here, I had to write an expression for the force in terms of F2, okay? So that when I find F1 in terms of F2, okay, then I can come and plug it into this equation and solve for F2. Okay, so let me plug in the numbers in this. And so if you do that, this is what you will get. E1 is the Young's modulus of steel. This is what it is here, multiplied by the cross-section area of the steel. We know the diameter of the steel, 15 millimeters. In meters is 0,015. So you square that, you multiply by pi by 4 to get the cross-section area of the steel, divided by the Young's modulus of the copper, E2. Okay, the copper is 2. Okay, so E2 is the Young's modulus of the copper, multiplied by the cross-section area of the copper. You know the diameter of the copper, 20 millimeters. So this is the cross-section area of the copper. And that's all multiplied by F2. And so from this, you can write that F1 is equal, when you work this out with your calculator, you will find that F1 is equal to 0,834 F2. Why is this important? It's because this will help us to solve for the forces F1 and F2 that are acting inside of each of these bars, okay? And so now that we know the relationship between F1 and F2, and we know also that F1 plus F2 is equal to 65,000 newtons. So, you see, so what you can do is replace now F1 here by this expression, 0,834 F2, okay? And then this equation will just have one unknown, which is F2. So if you do that, that is what you get here like that. And then you can solve for F2, and you will find F2 to be equal to 35,441.658 newtons. Once you have F2, then you know that F1 plus F2 is equal to 65,000. So F1 is therefore equal to 65,000 minus F2, and you have F2 here, so therefore you can find F1 as 65,000 minus that, which is F2. And you find F1 to be 29,558.342. Okay, so once you have F1 and F2, now you can find the stresses in the steel and in the copper bars, okay? The steel bar, you use F1, the copper bar, you use F2, and you divide by the cross-section areas, okay? Their respective cross-section areas. And so stress for steel is going to be F1 over A1. And if you do that, this is what you get. And again, here, this will give you a very large number in pascals. But if you convert it to megapascals, then you will get this, okay? And for the copper, it's going to be equal to F2 divided by A2. A2 is the cross-section area of the copper. And that gives you this. And again, this will give you a large number in pascals, but I converted it to megapascals, and this is what you get. And if you do that, that is what was required for the first part of the question. And for the second part of the question, you need to find the final length of the compound bar. Now, the shortening is x1, which is equal to x2, okay? So you can either do F1 L1 over E1 A1, or you can do F2 L2 over E2 A2. It's up to you. You will get the same answer because in this case, the shortening is the same for both bars, okay? So what you can do is x1 is equal to F1 L1 over E1 A1, and this is equal to x2, which is F2 L2 over E2 A2, okay? And so you pick, you can either use this one to find the shortening, or you can use that one to find the shortening. It's the same for both bars. Okay, so I picked the first one, and this is what I got. Okay, so F1 is this, we got it here. It's for steel, the force in the steel multiplied by the length of the steel bar, which is the same as the length of the copper bar, in this case, 0,127, because it's 127 millimeters. In meters, it gives you 0,127, divided by E1, which is the Young's modulus of steel, 215 gigapascals, multiplied by the cross-section area of the steel. And when you do the calculations, you get this in meters, and you can convert it to millimeters. That is 0,0988 millimeters. That is the shortening, okay? And the shortening of steel is the shortening of copper. They shorten by the same amount. You can see even by the arrangement here, that if you compress them, they will become short by the same amount, okay? And so to find the final length, since it's a shortening, you need to do the difference, okay? So the initial length is 127 millimeters minus the shortening in millimeters gives you this, okay? So I am doing my calculations in millimeters for the final length, okay? So 127 millimeters minus the shortening in millimeters gives you the final length of the object in millimeters, okay? Very important. Now, let us look at the testing of materials, okay, when it comes to tensile loading. And so usually in engineering, in order to be able to establish maybe the Young's modulus of a material, they will subject it to tensile testing. And so what is tensile testing? Basically, they will take a material, as you can see in the picture here. If you look in the middle here, you have a material. It seems to be made of copper or something like that, okay? You can see this material in the middle here, and it is held by clamps, okay, on both ends, okay? You have clamps holding the material on both ends, sorry, and these clamps will now begin to stretch the material, okay? So they will increase the tensile force on the material, and they will be stretching it. And as they increase the tensile strength, they will record how the material is behaving. And just by doing that, it is possible to establish what is the Young's modulus of the material, okay? So that is one of the things that tensile testing is used for, okay? And so what you need to know is, however, the graph, okay, that you get from this sort of testing, okay? You can either plot the load versus the extension of the material, like the load will be the force in kilonewtons, okay, or maybe in newtons, depends on the situation, versus the extension of the material, okay? Or you can plot the stresses versus the strain in the material, okay? It's one of the two, okay? So it's either you plot the load versus the extension of the material, or you can plot the stresses versus the strain, okay? And if you do that, generally you will get a graph that looks something like that, okay? It is not necessarily always like that, but it's more or less like that. And in this graph, you have some points that are points of interest. The first one is what I will call here point A. And point A is the limit of proportionality, or the elastic limit. In other words, here you have a straight line, okay? From the origin to point A, you more or less have a straight line, okay? So the load is behaving proportionally. Let me say, when you apply a certain load, the extension that you get is proportional to the load that you apply, okay? You have a proportionality going on here. But once you reach point A, that is the limit of proportionality. Okay, so let me just use examples to try and make it clear. Let's say if you apply 10 kilonewtons to this object, okay, you apply 10 kilonewtons tensile loads to this object. The object then stretches by, let's say, 1 millimeter. Then if you apply 20 kilonewtons, it will stretch by 2 millimeters. That is proportionality, okay? And so as the load is being applied, you have proportionality taking place for a certain period until you reach this point A. At point A, that is the limit of proportionality. Beyond point A, the behavior of the object is no longer proportional, okay? And so the way you know where the limit of the proportionality is where the curve ceases to behave as a straight line, okay? So you will see that from 0 to A, you more or less have a straight line here. But beyond A, you no longer have a straight line. It seems to behave now like a curve. So proportionality ends at A, okay? I hope that is clear. So A is the limit of proportionality. And B that you have there is called the yield point, okay? And the yield point is where now the material ceases to be elastic, okay? It's completely not elastic from point B onwards, okay? What is elasticity? Elasticity means that if you stretch the material, it will return to its original state. If a material behaves like that, it is elastic, okay? If you stretch it, it will return to its original state if you remove the tensile load. Then it is still elastic. But you get a point which is called the yield point, where if you stretch the material beyond that point, although it will return after you remove the tensile force, but it will not return exactly to the way it was before. Okay, so the point where that begins to happen, that is what is referred to as the yield point. Okay, and then you have some other points here. This is the point C. I am not going to get much into that because you do not really need to know much about that in this module. And then you have another point D there, but you have a point E, which is called the ultimate load or the maximum load point, okay? This is the highest load that the material is going to experience, okay? It's called the maximum load point or the ultimate load, okay? You will come across that expression, ultimate load. That is the highest load that the material experiences, okay? The highest load that the material experienced. That is the maximum load or the ultimate load. And finally, you have point F. Point F is referred to as the fracture load, okay? The load at which the material eventually breaks in two, okay? That is fracture. When it breaks in two, it is fracture. And so point F is fracture, okay? And so we can divide this curve into regions to facilitate understanding of what is really going on. So the first region is the elastic region that you see on the screen. And as I said to you, in the elastic region, if you stretch the material, when you let go of it, it returns exactly to its original length. Okay, and that region extends until you reaches the yield point, which is point B. Beyond point B, any further stretching of the material will result into yield, which means that the material will deform, and then when you let go of it, it will not go back to its original state, okay? And that kind of deformation is called plastic deformation, okay? Very, very important. So from here all the way to here, what you have is plastic deformation. Okay, so but let us look at what happens in the elastic region. Okay, so the material, what you see in gray here is just a piece of material. It will behave elastically. Okay, so if you stretch it and let go of it, it will go back to its original state. After that region, you have the next region, which is the yielding region. Okay, so in this region, it is yielding. Okay, if you stretch it, it will and let go, it will not go back to its original state. It will not return to its original state. So this is the yielding region. And then beyond that, you have another region which is called the strain hardening region. And here, as you continue to further stretch the material becomes slender. As you can see, this here is slender than that. Okay, it gets longer and slender. And then beyond the strain hardening region, you then get to the necking region. Okay, this region is called necking, the necking region, because you begin to observe now that as you continue to further stretch the material, that somewhere in the middle of it, it begins to take this shape. This is what is referred to as necking. I hope you can see that. And the reason it's taking this shape is because it's about to break. And finally, when you reach point F, which is fracture, that is where it is actually going to break. Okay, very, very important. And so, as I said earlier, the region here all the way to here is called the plastic region because In this region, any deformation that occurs is permanent. The object is not going to return to its final state. Okay, so elastic deformation is deformation that allows for the object to return to its original state if the load is removed. But plastic deformation does not allow the object to return to its original state once the load is removed. Okay, so here you will have permanent deformation, but in this region you do not have permanent deformation of the object. Very important. And so let us now speak of the factor of safety. So what is the factor of safety? Okay, as an engineer, you need to understand that if you are required to make a design of some sort, let's say somebody comes to you and say, I want you to design a chair that will be able to hold somebody that weighs 70 kilograms. So as an engineer, if you are wise, when you make that chair, you will need to make it at least to be able to hold even 100 kilograms. Because you do not want to design it exactly for 70 kilograms. Because what if that person maybe for some reason comes holding maybe a bottle of Coke and sits on that chair? If it was designed exactly for 70, now because he came sitting holding a bottle of Coke, the chair is going to break. So you don't want to design like that. It's not wise. It's not safe. So you always want to over design. Okay. And so that is what the factors of safety is about. It's about allowing for a certain extra amount of load to be carried by your design beyond what is the working load. The working load is what it will usually be doing, but you want your design to be able to carry more than the working load. Okay, and so that is what the factor of safety is all about. Okay, so if your design has a factor of safety of 2, that means that it is able to hold twice as much load as the working load, the load that it will usually encounter. It is capable to work with twice as much that load. Then the factor of safety is 2. Okay, I hope my explanation was clear there. And so in these kinds of problems, the factor of safety is given by this equation. It's equal to the ultimate stress divided by the working stress. Okay, this is the equation for the factor of safety. However, in engineering applications, we want to remain within the elastic region. Okay, and because we want to remain within the elastic region, therefore, the highest load that you have in the elastic region is the yield load, okay, the yield point or the yield stress, okay, and therefore our factor of safety equation generally will be equal to the yield stress divided by the working stress, okay, because in practical applications, it is often required that we remain within the elastic region, okay, because we do not want our design to begin to deform permanently, okay. We want it to remain within elastic deformation, okay, where it can go back to its original state. And so generally it is required that the material remains within the elastic limit. And if that is the case, then the factor of safety will be equal to the yield stress divided by the working stress. It's very important to take note of this. So when you're reading a question, if they tell you that they want you to remain within the elastic limit, when you're looking for the factor of safety, use the equation yield stress over working stress. Only use this equation here with the ultimate stress if in your question they gave you the ultimate stress and they did not speak of a concern to want to remain within the elastic limit. Okay? Very important. Okay, so let us look at this example here. A copper wire with a diameter of 4 millimeters and a length of 1.3 meters is required to carry a tensile load while remaining within the elastic range. The tension of the wire under this load must not exceed 1.6 millimeters. Now, I want you to notice that it is said that it is required to carry a tensile load while remaining within the elastic range. So they want to remain within the elastic range. Okay, so the extension of the wire under this load must not exceed 1.6 millimeters. The modulus of elasticity of copper is 90 gigapascals. That is the Young's modulus. Its yield stress is 100 megapascals, and its ultimate stress is 330 megapascals. Using a factor of safety of 3, calculate the maximum tensile force that can be applied to the wire. Okay, so here we have, in this question, we have two limiting conditions. The first limiting condition is that we do not want the extension of the wire to exceed 1.6 millimeters. The second limiting condition that we have is that the factor of safety must be 3. Okay? So we need to find a force that will satisfy both conditions. Okay? The extension must not exceed 1.6 millimeters, and the factor of safety must not be greater than, must be equal to 3, not greater, not smaller. Okay, so let us do that. So let's begin with the first limiting conditions, which is the extension of the wire must not exceed 1.6. We know the equation for extension or elongation is this, okay? X is equal to FL over EA. And so in this case, we can just go ahead and write F from this equation. We can rewrite this equation and make F the subject of the formula, and you will get this, okay? And from this, you can then calculate what the tensile load needs to be for you to achieve an extension of 1.6 millimeters. Okay, and so if you do that, you plug in the numbers, this is what you get. Okay, we know that the diameter of the wire is 4 millimeters. You change that to meters. This is the Young's modulus, 90 gigapascal, 90 times 10 to the 9. And this here is the extension, 1.6 millimeters, which is that in meters, and you divide by the initial length of the wire, which is 1.3 meters. And so for us to be able to have an extension of 1.6 millimeters, our force must not be greater than 1,391.97 newtons. Okay, but this is not the end of it, because not only do we need our extension to not be greater than 1.6 millimeters, but we also want our factor of safety to be equal to 3. Now, in this case, remember, I gave you two equations for the factor of safety. One was equal to the ultimate stress divided by the working stress. The other was equal to the yield stress divided by the working stress. Now, which one are you going to use here? Well, if you read the question, you will see that it is said that we need to remain within the elastic range. When there is a requirement to remain within the elastic range, then your equation for the factor of safety is the one with the yield stress over the working stress, okay? So, and from that, then you can write the working stress will be equal to the yield stress divided by the factor of safety, okay? And why do we need to find the working stress? It's because we will use that value for the stress to be able to determine the force, okay? Because force is equal to stress multiplied by area. But this equation for the working stress is coming from the equation for the factor of safety, where we want to remain within the elastic range, okay? Because factor of safety is equal to yield stress over working stress, okay? When you want to remain within the elastic range. And therefore, from that equation, you can derive an expression for the working stress like this. And the working stress will therefore be equal to the yield stress divided by the factor of safety. And here I just worked in megapascals to have my answer in megapascals. So the yield stress is 100 megapascals. divide that by 3, and that will give you this for the working stress in megapascals. And from there, you can get the force, which is equal to the stress multiplied by the area. And when you do that, this is the value of the force that you get, 418.875 newtons. Okay? And now, for us to be able to have an extension of wire that does not exceed 1.6 millimeters, we need our force to not exceed 1,391.97 newtons. For us to have a factor of safety of 3, we need our force to be 418.875 newtons. So now, which of these two satisfy both conditions? Well, if you use this force, when you try to find the factor of safety, you will get a factor of safety that is greater than 3. But we want our factor of safety to be 3. So this here will give you a greater factor of safety than 3. Okay, so this will not work. This will not work. Okay, you cannot use this force because it gives you a greater factor of safety than 3. But if you use this force, you will have a factor of safety of 3. And also the elongation is going to be smaller than 1.6 because the force is smaller than that force. And we want our elongation to not exceed 1.6. Okay, sorry, it's 1.6. Okay, so we do not want our elongation to be greater than 1.6. For that to happen, our force must be lower than this. And this here is lower than that. And this here also gives us a factor of safety of 3. Okay, and so therefore the force that we need that will give us a factor of safety of 3 and an extension that is not exceeding 1.6 millimeters is that force here, that force there, 418.875 newtons. Okay, I hope that is clear. Now let us look at this example here. Okay, this is a very long example. After a failure seen on a steering system tie rod, the manufacturers decided to perform a tensile test on a rod specimen to better understand its material capabilities. The diameter of the specimen is 21.5 millimeters and the gauge length is 90 millimeters. The following results were generated by the test. Okay, so these are all the results that were generated. You have the load at the limit of proportionality, the extension at the limit of proportionality, the load at the yield point, the ultimate tensile strength load, okay, the load at the fracture, the tensile extension after fracture, the diameter after fracture. Okay, so they gave you all the data. And now you have to calculate these things here. So let us get into that question. It's long, but it's actually very easy to do. Okay, so for question 1.1, you need to find the stress at the limit of proportionality. Okay, you know that stress is equal to force over area. Okay, so you will need to find the force at the limit of proportionality or the load at the limit of proportionality. LOP is limit of proportionality. And you divide that by the area, okay? And that will give you the stress at the limit of proportionality. So what is the force at the limit of proportionality? Is 113 kilonewtons. So you divide that by the cross-section area of the bar. You have the diameter, so you can do that very quickly, and this is what you will get, okay? For question 1.2, you need to find the Young's modulus of elasticity for the material, okay? So for you to get the Young's modulus, you will use this equation here. From this equation, you will be able to find what E is equal to. Okay, so E will be equal to that. And you can use, because to get the Young's modulus, you must be within the elastic limit. Okay, within that range. Okay, not beyond. You need to use data before the limit of proportionality or at the limit of proportionality. That is, any data there will help you get the Young's modulus. Since here we have data for the limit of proportionality, you can use them for calculating the Young's modulus. And so in this case, we will have the force at the limit of proportionality divided by multiplied by the length divided by the elongation at the limit of proportionality multiplied by the area, okay? So These here are already given, so you can just plug in the numbers, and this is what you will get for the Young's modulus, okay? For question 1.3, you need to find the yield stress. Now, how will you find the yield stress? Again, you need to find the load at the yield point, and this is it here, 258 kilonewtons, and that you will divide by the area, okay? So the yield stress is equal to the force at the yield point, the load at the yield point, divided by the area. And when you do that, that gives you the yield stress. Okay, for question 1.4, you need to find the maximum stress. Okay, the maximum stress is the ultimate stress. And so that is equal to the ultimate load divided by the area. The ultimate tensile strength load is given here as 449. So 449 kilonewtons, of course, you change that to newtons, that gives you 449,000, okay? And you divide that by the area, that gives you the ultimate stress. And as you can see, these things are really easy, okay? So the maximum stress is the ultimate stress, okay? Don't get confused because another term has been used. It's the same thing. And so for question 1.5, they need to find the breaking stress. Breaking is fracture. When the material reaches fracture load, that is when it breaks. Okay, so you are given the load at fracture, okay? And so you will divide that by the area at fracture, because remember, at fracture, necking has already began to take place, okay? So the cross-section area where it breaks is not the same as the initial cross-section area. So for breaking stress, the area that you will use in your equation is the area at fracture. And here it's given to you, the diameter after fracture is this. So you will use that for area, and you will use the load at fracture to find the stress at fracture, which is the breaking stress. And this is what you will have. And as you can see here, I used the diameter after fracture. I did not use the initial diameter, because when fracture occurs, necking has already begun to take place. So the cross-section area where it breaks is smaller, okay? And so the diameter is smaller, which is this here that I used. And I used also the load at fracture. And this then gives you the breaking stress, or the stress at fracture. 1.5. For question 1.6, okay, what we have to find is the percentage elongation. Okay, the percentage elongation is just given by this equation, okay? X over L multiplied by 100. Okay, that is the percentage elongation. And so if you do that here, X, the total extension after fracture is given like that. You can see it here. After fracture, this was the total extension of the bar. And so you divide that by the original length of the bar, you multiply by 100, and this will give you the percentage elongation. Okay? For question 1.7, what we need to find is the percentage reduction in area. And so that is equal to the initial area minus the area after fracture divided by the initial area and multiply it by 100, okay? This is what it is. And so if you plug in the numbers, this is what you will get, okay? And you will find 52.1% as the percentage reduction in area, okay? So I went very fast through this question because there really isn't anything complicated, but you are welcome to go through it at a slow pace with a pen and a paper to understand everything that I just did here. Now, let us look at our final example for the day, okay? So here, the data below is for a test piece, 250 millimeter long and 22.5 millimeter in diameter. So you are given a set of data from a tensile test where they applied loads and they looked at the extension of the bar, okay? So when there was no load, there was no extension of the bar. When they applied 30 kilonewtons, they observed 0.094 millimeter in extension of the bar. Okay, the units are written here. Okay, and when they applied 60, they observed 0.19 millimeter extension of the bar. When they applied 90 kilonewtons, they observed 0.284 millimeters in extension of the bar, and so on and so forth. Okay, so now you have these data from a tensile test. And now they ask you, from these, you need to plot the stress strain graph and use it to determine the following: 1, the Young's modulus; 2, the elastic limit; and 3, the yield stress. So you can see here you have a load versus extension graph that you can plot, but that's not what they want. They want you to plot the stress strain graph. So from these loads and these extensions, you need to find the stresses and the strains for each of the columns. Okay, and then you will create a table with stresses and strains, and then now you will plot the graph. And then from the graph, you need to find the Young's modulus, the elastic limit, and the yield stress. So let's go ahead and do that. So first, what we're trying to do is to plot stresses versus strain. That is what the question says. Okay? Some students don't read the question carefully and they go ahead, they begin to plot these data that they see here. And this here will give you a load versus extension graph. But you want a stress strain graph. Okay, so you can't plot these. But instead, you need to use these to be able to determine the stress and the strains, and then you will do the plotting, okay? So I already have my table here for stresses and strains, and now let us go ahead and find these values, okay? And so, what do we know about the stress? We know that the stress is equal to the force divided by the cross-section area. And you have a bunch of forces in this table. Okay, in this table you have a bunch of forces. So you will use each of these forces and divide by the cross-section area to find the corresponding stresses. And then the strain is equal to the elongation that you have divided by the original length. And in this table, we have a bunch of elongations for the various forces. And so we will take these, divide by the original length to find the corresponding strains. Okay, so let's begin with 0. Okay, when the load is 0, what is the stress gonna be? If you replace F by 0 in the equation for stress here, the stress, of course, will be 0. 0 divided by anything is 0. So we can come here, for 0, we will just write a stress of 0, okay? Because if the force is 0, the stress is 0, okay? Now, what will be the strain? If the elongation is 0, what will be the strain? If you replace x by 0, what is the strain gonna be? Of course, it's going to be also 0. So this here is also 0. So then we go ahead and do the same thing for 30. Okay, if our force is 30, what is our stress gonna be? Okay, of course, on top you will have 30,000 because it's 30 kilonewtons. We use SI units. On top you will have 30,000 divided by the cross-section area. And you are told that the diameter is 22.5 millimeters. You change that to meters and then you plug it into the equation for area, pi by 4 diameter squared, and divide the force by that cross-section area. That gives you the stress that corresponds to 30 kilonewtons. Okay, and that stress is 75.451 megapascals. And so you need to take that and you write it where you should write that value, which is here. Okay, and that is the stress that corresponds to that force. Now, what is the strain that corresponds to this elongation? The strain that corresponds to this elongation will be equal to 0.094. I changed it to meters because here the elongation is in millimeters. Okay, well, I didn't change it to meters, sorry. I kept it in millimeters, but I used also the length in millimeters, okay? But if you want, you can change all to meters, it's okay. But here, there is no need to do that because you can just keep the elongation in millimeters and use the length in millimeters as well, okay? So long as you are consistent with the unit in the numerator and the denominator. So the elongation was 0.094 millimeters, dividing it by the original length, which is in millimeters also, 250, it's given there, okay? So if you divide the elongation by the original length, then you get the strain, okay? And the strain is equal to 0.000376. As you can see, that is a very small number. If you want to plot that, it can be a bit complicated. That is why here, for my strains, I multiply every number by 10 to the minus 6 so that I can have big numbers here that will make it easier for me to plot. Okay, so for instance, instead of 0.00376, I wrote 376 here, but I did specify here that in this row for strain, every value must be multiplied by 10 to the minus 6. So if you multiply 376 by 10 to the minus 6, then you get the actual value for the strain, which is 0.000376. Okay, so this is how you do it, and you need to do it for all the values in the table, all these values. Now, if you do that correctly, this is what your table is going to look like, and these are the values that you're going to get. And now you can plot, okay, because you now have stresses and you have strains, and you can plot. And you know that the strains are always on the horizontal axis and the stresses are on the vertical axis. So what I did, I labeled my horizontal axis strain multiplied by 10 to the minus 6, okay? And then the vertical axis, I labeled it stress in megapascals, okay? So that I can just plug in the values as I read them in the table. And then I had to divide my axis. So of course you have 0 there. I hope you can see you have 0 here. And then you have all the divisions. I divided them in thousands, in increments of 1,000. And then on the vertical axis, I divided them in increments of 50 megapascals, okay? And it goes up like that. And so now I need to plot, okay? So the first point is 0, 0. Where is 0, 0? 0, 0 is here. So that will be my first point. You can see 0, 0, that blue dot. Okay, that's my first point. The second point is that on the horizontal, I have 376 and the stress is 75, okay? So 376 should be like somewhere here, okay? And 75 on the vertical is like somewhere there, okay? So if you plot it, 376 is on the horizontal, 75 is on the vertical. If you plot where they meet, it's like somewhere there, okay? And so that is where you will have that point, okay? 376 and 75. The next one is 760 and 150. Where is 760 and 150? It's there. You can see here, this should be something like 760, and then we go up to 150 point something, it's there. And so on and so forth, okay? So you go like that and you plot all the points, and you will get these points looking like this, okay? And then now you need to join them with a line, okay? And this line is your stress strain curve, okay? If you do it, this is what you will get, okay? And so once you do that, you have plotted the stress strain graph, and now you have to use it to determine the Young's modulus. For you to find the Young's modulus, as I said in the previous example, you need to pick a point that is within the elastic limit. Any point within the elastic limit can help you find the Young's modulus. You can take the point at the limit of proportionality or any point before that, okay? And as you can see, if you look carefully at this graph here, you will see that we have a straight line from here until here, okay? So this point here is the limit of proportionality. From here, as you begin to go further, it begins to bend. It's behaving like a curve now. Okay, so the limit of proportionality is here. Okay, because from here to here, we have a straight line. So you can pick any of these points here to try and find the Young's modulus. Okay. And so for me, I decided to pick the first point. Remember that stress is equal to Young's modulus multiplied by strain. Therefore, Young's modulus will be equal to stress over strain. And I just picked this first point, which is this point here. If you want, you could also pick that point to try and find the Young's modulus. And you could also pick this point because this is the limit of proportionality. But you cannot pick these other points here because these other points here are beyond the limit of proportionality. But you can pick this point, or this point to try and find the Young's modulus. Of course, you're not going to get the exact same number, but it will be around the same number. And whatever point you pick, so long as you are within the limit of proportionality, you will get the marks, okay? Because you need to be within the limit of proportionality for you to find the Young's modulus. Okay, so in this case, for me, I just picked this first point here and I used it. The stress at that point is 75.451. The strain, we calculated at 76 times 10 to the minus 6, which is this. And so you can divide the stress by the strain, and that gives you the Young's modulus, approximately 201 gigapascals. Okay, so now, we need to find the yield stress. From the graph, the yield stress, you can read it where all of a sudden there is no proportionality. Okay, the point from which there is no proportionality, the point where all of a sudden the extensions are increasing rapidly. Okay, so if you look at this graph here, you will see the limit of proportionality is here. Okay, so from this point here, there is no more proportionality. So this is what your yield stress is, okay? And you can also see here in the table, from 0 to 30, it increases. It went from 0 to 0.09, and then from 30 to 60, it increases to 19 and then to 28. But then when you come here, you will notice that here it went to 0.4. It's like it increased much, okay? And so you can see already that this point here, which corresponds to 289.229 megapascals, okay, this point, that is where the yield stress is, okay? As soon as proportionality is no longer there, that is where you will find the yield stress, because you can see that the elongation is beginning to increase rapidly from that point. And so in this case, therefore, the yield stress... Oh, okay. Question number 2 was the elastic limit, okay? I was explaining to you the yield stress. So let us go, and this is the yield stress, which is what I was explaining to you, okay? 289.229, okay? That is the yield stress. And all that explanation was for the yield stress, okay? But now going back to question number 2, the elastic limit, okay? The elastic limit is the limit of proportionality. In this case, it is here, okay? And as you can see here, we are at 200 and something megapascal, which is 226.353 megapascals, okay? This is the limit of proportionality. That is the elastic limit. That is where it ceases to be a straight line. So it is a straight line until that point. That is where the elastic limit is, okay? And that is that. Okay, so I hope this video was helpful to you. Do not get confused. Again, here I went ahead of myself. I started speaking of the yield stress instead of the elastic limit. It was a long video. I'm beginning to get tired. But here, question number 2 was the elastic limit. And the way you find the elastic limit is that you look at the limit of proportionality, where the straight line ends, okay? If you look at this graph, you will see that it ceases to be a straight line at this point. From this point, it's beginning to bend. So this point here is the limit of proportionality or the elastic limit. Okay, and if you look at this point, it's the fourth point on the table. So it's 1, 2, 3, 4. So it's 226.353 megapascals. That is the elastic limit. And for question number 3, it's the yield stress. And that, as I was explaining, you need to look for the point where it is beginning to increase rapidly. The extension is beginning to increase rapidly. There is no longer proportionality. And if you look at that point, proportionality stops here. From here, there is no longer proportionality. And even when you look in the table, you will see that from 115, the extensions is beginning to increase rapidly from that point. And so that is the point where you have the yield stress. So the stress that corresponds to 115 is actually 289.229 megapascals. That's the stress corresponding to 115 kilonewtons. And at 115 kilonewtons, that is where the elongation is beginning to increase rapidly. Okay, so that point there, which corresponds to 289.229 megapascals, is the yield stress, which is here, okay, which you can see on the graph here. That is the yield stress. Okay, so I hope this video was helpful to you. Please just subscribe to the channel, like the video, leave a comment. This encourages me really to continue to make content of this nature. And if you wish to get in touch with me, please feel free to contact me using the number in the description.